So in the previous session, we had discussed about liquid-liquid extraction and solid phase extraction. In today's session, we'll try to understand what is the role of buffer in various extraction process. And we will also try to understand the role of salts in the extraction of the analytes or the biomolecule of interest. So we know that a buffer is a mixture of weak acid and its salt, or a weak base and its salt. As a biochemist, when I try to perform any extraction process, cell lysis is one important stage wherein the cells are broken and we obtain the lysate. And one of the most important elements of a successful lysis is dependent on the extraction buffer, or we also call the extraction buffer as lysis buffer. So what is exactly the role of the lysis buffer or the extraction buffer? The lysis buffer, what we use largely depend on the localization of the analyte, or more specifically, say for example, we can take it as protein. So if you are trying to isolate a protein, maybe of very significant value or maybe of therapeutic value, now when it comes for isolation of the protein of interest, the lysis buffer what you choose, it largely depends on the localization of protein. And second thing is, these buffers, they contain salts which regulate the acidity and osmolarity of the lysate, which is very, very important, because you are trying to extract a biological macromolecule wherein if the macromolecule is a protein, definitely you will be interested to retain the native conformation of the protein without loss in biological activity. So we know that the buffer contains salts which regulate the acidity and osmolarity of the lysate. So normally the extraction buffer or the lysis buffer, they work at an ionic strength ranging from 0.1 to 0.2 molar, and the pH range is from 7 to 8. Why this range is given for ionic strength as well as for the pH? Because this is considered to be the most compatible range of ionic strength and the pH with that found inside the cell. So each buffer what you choose for the lysis, it has a specific pH range. So whenever you choose a lysis buffer, keep it in mind that it should be based on whether the target analyte, in our case we are discussing about the isolation of the protein of interest, whether the target analyte is or will be stable within the given specific pH range. So you should choose the lysis buffer which has a pH range where the target analyte is stable in that pH range. Right? So essentially the cell lysis is the breaking down of the cell membrane and the separation of proteins from the non-soluble part of the cells, because we have taken protein as an example. So lysis buffer contain different detergents. We had discussed about different detergent in the previous class. So we know that these detergents, they help to release the soluble proteins. So it can be Triton X, Tween, SDS, CHAPS is available. So lysis buffer contain different detergents that help to release the soluble proteins. Dependent on the location of the protein of interest, a different lysis buffer is needed to obtain a high yield and purity of the analyte or the protein in our case. So the choice of the lysis buffer depends on the location of the target molecule. So it is not a set standard lysis buffer composition which can be used for all kind of extraction. No, it is not so. Depending upon the location of the target molecule, where exactly the target molecule is. See, in this table you can see the target molecule location can be within the whole cell, or it can be a membrane bound, the nucleus, in the cytoplasm, in the mitochondria. So a different lysis buffer is needed to obtain a high yield and purity of the target molecule. It is not that you can use a buffer for all of the locations, but you will not get a high yield and purity cannot be expected, because a composition of lysis buffer which is very good for membrane bound may not extract the analyte in large quantity and highest purity if the analyte is present somewhere in the cytoplasm or mitochondria, because the lysis buffer is very well suited for membrane bound proteins, may not be that good for cytoplasmic or mitochondria. That is the reason why a different lysis buffer composition is needed to obtain a high yield and purity of the target molecule. However, every protein is different and you can expect that they may react differently with the buffers and detergents. So if you don't get your protein of interest into the solution, so you have to try different buffers and exchange of the detergents. So it is not only from the composition of buffer side, it is also from the protein. Each protein is different and each protein react differently with varying composition of the buffers and detergents. So if when you are performing an extraction procedure, if you are not able to get the protein of interest into the solution, or if you are studying a protein-protein interaction study methods, if you are using protein-protein interaction methods, then you are not getting protein of interest. That means you have to try different buffers and exchange of detergents. So I have given a general approach in this table. If your protein is cytoplasmic, then you can probably use the Tris HCl lysis buffer. This is recommended. And if your experiment requires solubilization of your protein, that means if you want to solubilize the protein, then a slightly harsh buffer or hard buffer which contains detergent can be used. And the typical example is RIPA buffer, that is a radioimmunoprecipitation assay buffer. So this RIPA buffer is used to lyse cells and tissues, specifically for use in radioimmunoprecipitation and also in protein assays, protein purifications, and other analytical procedures. So this RIPA buffer can disrupt nuclear membranes and it can solubilize cytoplasmic proteins. So when it can disrupt nuclear membranes and it is having the ability to solubilize cytoplasmic proteins, so definitely the resultant lysate will be higher in protein yield. So one of the best buffer system where you can expect higher protein yield. And in the detergent table which we discussed in previous session, you could if you can remember, we mentioned about NP40. So these are non-ionic detergents, that is nonidate P40, which solubilizes both the plasma membrane and membranous organelles, but they do not disturb the cytoskeleton. The cytoskeleton will be intact because it is a very mild and it is a non-ionic detergent. And this is very much ideal for whole cell lysates, and it is sometimes used for membrane bound proteins. If you are looking for some of the membrane bound proteins, trying to extract such proteins, or maybe if you are interested to isolate proteins from that cytosols. So you can make use of the NP40, which is a mild non-ionic detergent if you are working on whole cell or some membrane bound proteins or cytosolic proteins. Then more frequently used in cell lysis is the CHAPS. Again, CHAPS is a non-denaturing Zwitter ionic detergent. So this has the ability to solubilize membrane proteins and it maintains some degree of protein-protein interactions, and it can disaggregate the protein complexes without affecting the secondary or the tertiary structures. But there is one limitation for the use of CHAPS in protein isolation. That is, the CHAPS disrupts protein-protein interactions, so it is not at all recommended if you are studying the co-immunoprecipitation methods or using the co-immunoprecipitation methods. That means if you are working on co-immunoprecipitation, then the use of CHAPS, because it disrupts the protein-protein interactions, it is not recommended. Right? So now we'll try to understand what is the role of salts in extracting the biomolecules. So again, we'll continue taking protein as example because that is very much easy to understand. So from the literature, it is known that the salts affect the properties of macromolecules. And it affects in a very different manner, widely different manner. It is not a single point which is showing this is the property of the macromolecule that is changed as soon as you add the salt. No, there is a different manner where the properties of the macromolecules are affected when salts are present. Number one, stability. The number one property of the macromolecule which changes in the presence of salt is number one, stability. Salts may increase the stability of the macromolecule that we are trying to extract. And number two, solubility, because this is very, very important. If you cannot solubilize the molecule of interest, then there is no point in extracting. And number three, the biological activity. So the macromolecule should retain the biological activity. Number one, stability is very, very important. Solubility is also important, and biological activity is equally important. So these are the important properties of any macromolecule, be it protein or whatever it is. So salts have a role to play when used in extraction. So how do the salts affect the properties of the macromolecules when present at low concentrations, also when present at high concentrations? When they are present at low concentrations, they stabilize proteins and other polyelectrolytes. And the reason for this is non-specific electrostatic interactions. What happens if it is present in high concentrations? Definitely stability should not be lost. So they result in stabilization of the macromolecule. But there is an added property coming in, the denaturation. Yes, there is a threshold concentration, threshold level for the presence of salt in the extraction buffer. If you increase the salt concentration above the threshold level, then the salt denatures the macromolecule or the protein. So the denaturation of the macromolecule in the presence of salt is dependent on the nature of the salt what you are using, and number two, on the concentration of the salt. So two important points should be remembered over here. What is the type of the salt that you are using, and what is the concentration of the salt you are using? Basically, salt stabilizes the proteins and polyelectrolytes. But if you cross the threshold limit, at threshold level or the limit, depending upon the nature of the salt and its concentration, denaturation of the proteins or the macromolecule can occur. Right? So now the question is, how does the solvent-induced interaction between solute particles vary when salts of different types are dissolved in the aqueous solution? In order to understand this and answer this, we need to know what is the role of protein solvation. Could be a new terminology, but the method wise it is not new. You are quite aware of the solvation process. In most of the time, the proteins what we are trying to extract, that needs to be concentrated, and it has to be taken for further analytical steps. That means you may get proteins along with some salts, or maybe the protein may be in very low concentration once you extract from the lysate. So you need to concentrate that so that you get only the protein to take it further for HPLC analysis and then mass determination in the mass spectrometer. So there are several techniques that are available to do so. Number one, ultrafiltration. Number two, affinity chromatography. And number three, precipitation. So what we are trying to understand here is what is the role of salt in the extraction of macromolecule. In order to understand that, we need to know what is the role of protein solvation. So I said, whenever you extract a protein, you need to concentrate the protein. How do you do that? You have to either use ultrafiltration or affinity chromatography or precipitation. So protein precipitation, when compared to ultrafiltration and or affinity chromatography, exhibit relatively poor recovery. So the recovery is very less in ultrafiltration and other techniques. Even though there is development of new materials that are used in ultrafiltration, a significant amount of proteins can non-specifically stick to the ultracentrifugation membranes. Right? So proteins may also stick to some degree of the sorbents or the stationary phases used in affinity chromatography. So you may lose the quantity of the protein. That means the yield will be very less. That's what. There is relatively poor recovery of the proteins. But precipitation is believed to yield the highest recovery and is suitable for low volume protein extracts. So the basic principle of precipitation, we'll try to understand precipitation as an important component in the extraction process. So precipitation, though it is believed to yield the highest recovery, it is also believed to be the best for or the best method for low volume protein extracts. The basic principle behind this precipitation is that it alters the solvation potential of the solvent, and number two, it lowers the solubility of the solute by addition of a reagent wherein we refer to as precipitating agent. Right. So the solubility of proteins in buffers depends on the distribution of hydrophilic and hydrophobic amino acid residues on the protein surface. That means the hydrophobic residues, they predominantly occur in the core, but some do exist on the surfaces. So proteins which have high hydrophobic amino acid content on the surface, they have low solubility in aqueous solvent. So you should remember this always. That is, I'll repeat, the solubility of proteins in aqueous buffer depends on the distribution of hydrophilic and hydrophobic amino acid residues on the protein surface. Now, the hydrophobic residues, they are present in the protein core, but some residues do exist on the protein surface. So proteins which have high hydrophobic amino acid content on the surface have low solubility in any aqueous solvent. So the charged and polar surface residues, so they interact with the ionic groups in the solvent and they increase the solubility. Now what is required? You need a prior knowledge. This is the prior requirement. You need to know what is the amino acid composition of a protein. That leads to determination of an ideal precipitation solvent and the method of extraction. Because proteins which have high hydrophobic amino acid content on the surface have low solubility. And charged and polar surface residues interact with ionic groups in the solvent and they increase the solubility. So whether hydrophilic residues are present on the surface or hydrophobic residues are present on the surface, so this knowledge, the knowledge of amino acid composition of a protein, determines an ideal precipitation solvent and method of extraction. The repulsive electrostatic forces which are in place during the dissolving of proteins. So these repulsive forces among the proteins, they prevent aggregation and in turn they facilitate dissolution. So you can see proteins entering into the solution. Now the solvent counter ions, where you can see over here, they migrate towards the charged surface residues on a protein and there they form a rigid matrix of counter ions which are attached to the protein surface. So the adjacent solvation layer, which is supposed to be a less rigid, it consists of decreasing concentration of counter ions and increasing concentration of co-ions. So what is the effect? The potential of proteins to engage in ionic interactions with each other will decrease. So they cannot engage in ionic interactions with each other. So this result in lower chances of forming aggregates. That means they will be in solution. So in this example, you can see the water molecule. So as they form a solvation layer over here around hydrophilic surface residues of a protein, thus they establish a concentration gradient around the protein with the highest concentration at the surface. So what happens? So this water network it has an impact on the attractive forces between the protein molecules. Say, for example, basic residues on a protein can have electrostatic interactions with acidic residues on a different protein molecule. If this protein molecule has basic amino acid residues on its surface can have an electrostatic interactions with this protein molecule, assuming that there are acidic residues on the surface of this protein molecule. However, the solvation of ions in any electrolyte solution, or be it with water, it will decrease the protein-protein attractive forces. So if you decrease the hydration layer, if you just decrease this layer, what happens? Because of more hydration, there is no protein-protein interaction. If you decrease this layer by adding precipitating agents, so then what happens if you add this precipitant? So this reagent around the protein enhances protein accumulation and facilitate precipitation. So this protein precipitation occur in a stepwise manner. That means you need to add a precipitating agent and you need to mix steadily so that the precipitant and target molecule collide, destabilizes the protein solution. So what exactly it is happening when we add salt? What happens is that, say for example, we'll take ammonium sulfate. So when we add ammonium sulfate to a protein present in a solution, now what happens when we add ammonium sulfate at low concentration, keeping this basic principle of protein precipitation mechanism? At low ammonium sulfate salt concentration, we see an effect which is called as salting in. So what is happening in salting in? Because we are commonly asked about two parameters when we work on protein extraction. Is it salting in method or salting out method? So I'll just elaborate on these two methods. When we add ammonium sulfate, we are taking ammonium sulfate as an example. So when we add ammonium sulfate at low concentration, we see an effect called salting in. Now what is this? What is happening in salting in process? Here the solubility of the protein increases. How the solubility of protein is increasing? I'm just discussing the same concept in a very simple language. So at low salt concentration, salting in occur. That means the solubility of the protein increases. How does this happen? So what is happening here is that ions from the salt, they associate with the surface of the protein. So when they get associate with the surface of protein, this shields those areas from the water molecule. So water molecule cannot have access. In effect, this means that less water molecules are required to interact with the protein surface and the concentration of free water is more. In other words, we say that the activity of the water has increased. So what is the net effect? Net effect is that the protein becomes more soluble. This is referred to as salting in. Here the salt ions associate with the surface of the protein. So there is a masking or shielding of those areas from water molecules. The water molecules cannot go and associate with the surface of the protein. So less water molecules are required to interact with the protein surface, and the concentration of free water, that means the water molecule not interacting with the protein surface, it is increased. That means water activity has increased. So the net effect is that the protein becomes more soluble. This is observed when the salt is at low concentration. What happens at higher concentration of salt? We see the reverse effect, that is salting out. Now what's happening now here is that all the binding sites on the protein surface for the salt ions, they have been occupied. So the ions begin to interact with the solvent itself. Here the solvent is water system. So the salt ions at higher concentration. So first what the salt ions do, they interact with the surface of the protein, that is on the surface residues of the protein, and over and above still there are salt ions. So now they begin to interact with the water molecules. So the concentration of free water molecule decreases as they are used to solvate the salt ions. So the protein molecules move closer together and they begin to interact with one another through hydrophobic or charged patches on their surfaces. So at some concentration of the salt, that is at some threshold concentration of the salt, as I said in the beginning, depends on the nature of the salt and the concentration of the salt that is being used. The protein molecules aggregate and they easily come out of the solution. So this is referred to as salting out of proteins. Right? So as I said, salting out is a process when the appropriate concentration of the salt is reached in solution. That means above the threshold level. Right? So here are some of the examples of the chaotrophs and the kosmotrophs. You can see the chaotrophs, so they show weak interaction with water, and we have kosmotrophs where they show strong interaction with water. I just explained what salt ions, or what is the net effect of salt ions when they show weak interaction or strong interaction with water, and these show negligible effect. And in this image you can see the properties of these ions. Here these ions which are green in color, so they have higher surface tension. The solubility of proteins is decreased, that means salting out happens. Protein denaturation decreases, it is very good. There is increase in protein stability, which is also a good property when we isolate or extract the proteins. Ideally, this is very good. Here, these ions have higher surface tension not as compared to these ions. Solubility of proteins increases, that is salting in take place. Protein denaturation happens when protein is in solution for long period. Decreases protein stability. Protein denaturation is increased, so naturally the outcome will be decrease in stability of the protein. So in salting in and salting out graph, you can easily make out this axis indicate increasing concentration of the salt being used in extraction against the solubility parameter. So this is supposed to be the protein molecule and this is the salt ion. So as the salt concentration increases over time, if you increase the salt concentration, naturally the solubility keep decreasing. That means you see the protein coming out of the solution. So this is referred to as precipitation area. This is referred to as solubilization area. Okay. So next we have another form of precipitation, which is referred to as isoelectric point precipitation. So we know that the isoelectric point or the PI, it is the pH of a solution at which the net charge of a protein becomes or it is 0. But at the PI value, the negative and positive charges are balanced. That is known. So the effect is it reduces repulsive electrostatic forces and the attraction forces predominate. So this causes aggregation and precipitation. So ideally the PI for most of the proteins is in the range of 4 to 7. And if you want to precipitate, you can make use of hydrochloric acid or the sulfuric acids. And the disadvantage of the isoelectric point precipitation method is the irreversible denaturation caused by the use of the mineral acids such as hydrochloric acid and sulfuric acids. So for this reason, isoelectric point precipitation is used, but most often it is used to precipitate the contaminant proteins rather than the target protein or protein of interest. So we are speaking about various precipitation method because we saw that precipitation is supposed to be the best method because it gives or the yield is very higher and you can expect a good or the purity of the molecule is very good. So we are trying to understand various precipitation methods that are available to extract the protein of interest or the molecule of interest or the analyte. So we have isoelectric point precipitation, but the disadvantage is it causes irreversible denaturation because we are using acids such as hydrochloric acid and sulfuric acid. So you can make use of this method to precipitate proteins, but to precipitate the contaminant proteins rather than the target protein. Next, we have organic solvent driven precipitation. So when you add miscible organic solvents such as ethanol, we have methanol or acetone is also used. So they cause proteins in solution to precipitate. How do they do that? The solvation layer around the protein will decrease as the organic solvent progressively displaces water from the protein surface. So when you see, there is a solvation layer around the protein. So when you start adding the miscible organic solvents, these are all the example of miscible organic solvents. In organic solvent driven precipitation, we use miscible organic solvents. So these miscible organic solvent molecules, they progressively, slowly displaces water which are found on the surface of the protein and binds it in hydration layers around the organic solvent molecules. So with smaller hydration layers, the proteins can aggregate by attractive electrostatic forces. Now, there are some important parameters to consider. That is number one, temperature. When you use organic solvent driven precipitation, temperature should be less than 4 degrees centigrade. Ideal is 2 to 4. So that you can avoid denaturation. And number 2, pH. And number 3, protein concentration in solution. So these are some of the important parameters that need to be considered when you are looking for organic solvent driven precipitation. We have trichloroacid precipitation, TCA precipitation, commonly referred to as TCA method. It is supposed to be a very effective protein precipitating method because TCA is a strong precipitating agent, especially when you are using dilute solutions, dilute extract solutions. But how TCA proves to be effective protein precipitating agent, the mechanism is still, or we know very little about the precipitating mechanism. But what is known from the literature is that roughly 15% of TCA is required for hydrophobic aggregation. So this is experimentally determined percentage of TCA that is required for hydrophobic aggregation. Otherwise, how exactly the TCA show the precipitation mechanism is yet to be determined because of less studies on the mechanism of the precipitation using TCA. Now, the most important component in any extraction process is how to choose a solvent system. Which is the best solvent for my extraction? How to determine which solvent should I choose? Because we know there are several category of solvents and each biomolecule behaves in a very different way in various solvent system. So what makes a solvent the best solvent for extraction process? What are the properties of a solvent system that I have to look in in order to employ that solvent for extraction process. So I'll just list the properties and we can discuss about each of the property little later. So number one, it's about solubility. Number two, it's about distribution coefficient. Number three, selectivity. Number four, immiscibility. Number five, chemical reactivity. Number six, viscosity, boiling point, and vapor pressure. So this is a table which gives you a list of solvents. You can just glance through this, and various properties are given over here for each of the solvent system. You can get it in any of the textbook or in any of the research literature. Now, what is the relevance of solubility in choosing the solvent system? Solubility is supposed to be the first property that we must consider in deciding the applicability of a solvent, because it refers to the ability of a solvent to dissolve considerable amount of the analyte. If you have chosen a solvent wherein the analyte is not soluble, then the extraction process is of no use. So the important and first property that we have to look in when deciding the applicability of solvent system is the solubility, because this is the one which referred to the ability of a solvent to dissolve a substantiative amount of the analyte or the molecule of interest or whatever it is. So the solute should be very soluble in the solvent phase. If it is not soluble, then the property is attributed to thermodynamics. Right. So let us not go into the thermodynamic approaches why the solvent is not capable of dissolving a particular analyte. But for now, we'll restrict our discussion that these are some of the important, these are the list of properties, ideal properties for the solvent system to be used in extraction process. And the first property to be considered is about the solubility, because this is the one property where you find the ability of a solvent to dissolve a quite good amount of the analyte. And second property is about the distribution coefficient. So what is distribution coefficient? It is defined as the ratio of total concentration of solute in organic phase to the total concentration of solute in the aqueous phase. So it is giving you a measure of the difference in the solubility of the solute in organic phase as well as aqueous phase. That means a higher distribution coefficient value implies that the solute has higher affinity for the organic phase. So the higher distribution coefficient means more easily the solute will be extracted into the organic phase. So this is again an important property to be considered, right? So I'll stop my discussion for now. We'll continue our discussion in the next session. Thank you very much.